So yeah, my talk is on hardware backdoors, hardware attacks, as well as supply chain attacks and how they all work together. And then we'll also be discussing some elements of firmware attacks as well and how those play a part. And to do this, we'll go through a few different examples of how these look and how you can defend against them. So just a little bit about me first. My name's Sophia, and I run a small cybersecurity company in New York called Margin Research, as well as work extensively with Riverloop Security. So most of this work in this presentation was done in conjunction with them. My co-speaker, Jeff Spielberg, who works at Riverloop, couldn't be here today, but this is also part of his work as well. So all these images are just kind of other places that I've worked with in the past or work with now. I recently published an article on Lawfare about backdoors and how it relates to base stations and 5G, more from a policy angle, but as we'll see coming up, a lot of that plays a part. All right, so to go through the hardware threats, let's first look at the standard stack. So we have our data applications, we have our virtual machines, operating systems, and everything else underneath that. And for the most part, we're pretty good at protecting from threats against these. We know how to write signed code. We know how to do as ASLR. We know how to check for binaries that might have inconsistencies in them or vulnerabilities. And we know how we can carry on those security measures through different applications. So the one that I like to give is once you reverse engineer application and you say, okay, this is a good application, this is the correct one, you can simply take a hash of that and check that against the hash that you've pulled off firmware or pulled off devices going forward. And all you have to do is check the hash matches, and you have a pretty good assurance that the security properties that you've guaranteed carry forward into that. But one thing that's really fallen under the bandwagon is hardware verification. And the main reason for this is that hardware verification is mostly outside of a company's control. So a company providing you with a router or a computer doesn't necessarily have the ability to protect you against external threats. So on the left, we see here maybe wiretapping, and on the right, we see these physical peripheral devices, which I'm sure most of you guys are familiar with, and we're pretty familiar with those. And then we can go to lower grained ones like sock implants, system on chip, which is basically when an implant is inside of another chip. So it's not unreasonable that a radio is inside of the same chip packaging as a microcontroller. They already make chips that have these two components together. Packaging them all at once saves money, and oftentimes they'll be shipped this way, and only one thing will be connected to the actual device. We also have PCB implants as well, which I'm sure everyone's aware of, was the alleged Supermicro attack. Oh, sorry, that was the wrong picture. There we go. So you can see here that the alleged Supermicro attack, which was gray or off-white in color, and looked like a signal conditioning coupler, was actually implanted on a PCB. And this is unlikely to be detectable without specialized equipment or the ability to crack open and look at all of your devices. All right, so I'm just going to go through a few different types of potential hardware implants. So I call this one the sandwich. This is not the official name of it, but it's basically when you have a 3D packaged chip with through silicon vias. So we see here, these are through silicon vias. I'm not sure if you guys can see my mouse or not, but they contain one or more chips integrated in a stacked fashion, so like a sandwich. And simply the attack would go like this, where you have a package substrate and additional vias that are connecting things that shouldn't be inside of the chip or inside of the packaging. And optically, when you look at the chip, these are really hard to detect. So even if the chip has to be opened up and this has to be sandwiched inside of it, there's going to be a little seam on the edge of the chip, but this seam is already there usually, and so it really wouldn't tell you anything. Additionally, when you look at this sort of component through an X-ray, the solder balls mask things, and there's actually no footprint through a traditional X-ray, or how you would traditionally look inside of a chip. So yeah, the pro of this attack is that it's logistically easier than wire-bound implants. And there's no really package to reverse engineer. And these sort of chips are very common in mobile devices right now, as well as we started seeing them pop up in servers. And also graphics chips also used through Silicon Via. So in general, this sort of packaging is faster, so things are closer together, as well as cheaper to manufacture because the width and the size of the chip stays the same. However, to perform this kind of attack, you need to actually perform custom through Silicon Via layer development, and you'd actually need a mid-100K fab to do this. So it'd be pretty costly. So this slide is actually taken in part from Bunny's talk, which I recommend everyone go watch. And he gave his talk at Blue Hat Security, the Microsoft conference. Yep. And so one thing I like to point out from this is Intel unveiled a new 3D packaging chip last year. They literally had, if you go look online, a part about security, and the circuit security is defined as security through obscurity because of this 3D integration being very hard to reverse engineer and to verify. All right. I'm not sure if we're taking questions during this, but I will try. I think there's questions. I don't know. We'll look at questions at the end. All right, so the next type of attack that I like to describe is called the ad. So this is what the Supermicro attack was, and it was basically something that was on board. So something that shouldn't necessarily be there, or is a component that's different than what the specification entails. However, the problem with this is they can be legitimate. So you can move a component from one pad to another and have it perform the same operation, but it's different than the spec. Things that end up being cheaper if you swap out components. Perhaps a component actually isn't available through the supply chain, and the manufacturer is forced to use a different one. And so in general, this is pretty common. So even if the component is new or different from what the specification entailed, it doesn't necessarily mean you have a problem with security. It just means that the manufacturer decided that was the right way forward. All right, and so we're looking at this through X-rays right now. This is an ad inside of an integrated circuit. The problem with this is this is the X-ray. You can't see a image top down on PCB. So we can extract this and throw it through an X-ray, but looking at the full PCB through an X-ray is very difficult. We also can't see the image side on a PCB. And so it's actually quite hard to determine what's actually going on. So for example, here we have to look at the side of the chip to actually see what things are connected. And also, like I said, things can be legitimate. So it could be a flash memory package that was added. Different configurations or different things were connected, even though it's the same chip that was used on 1,000 other different hardware pieces that were shipped off the same manufacturing line. And so it's wire bound differently, but it's the same. So it's all very difficult to determine what inconsistencies are malicious and what inconsistencies are just intentional by the manufacturer or honest mistakes. However, if a single contractor does try and modify the board or modify the spec at manufacturing time, there's many different stages of verification and checks in the plant that it has to go through. And so more often than not, it wouldn't be able to pass through inspection. So these sort of attacks are quite hard to pass through. As we can see here, yeah, it's a pretty complex system. So that's the board side of things. I go into this more in previous talks I've done, like the last one at KernelCon, if this is of interest to people. But I wanted to highlight one specific type of attack, so TPM attacks. This seems to be a popular topic right now. And so it's by definition, TPM is a root of trust of a given system. And it's trusted because its correct operation cannot be verified by that system. So in general, for a CRTM to operate correctly, it must be immutable for the system that relies on it. And so this just means that this part is considered trusted and can't really be verified by the person auditing or by the person reverse engineering the board. However, as we know, after this point, each stage after that should be verifiable. And as we see here and see how it's used in practice, usually for bootloaders and things, every stage is verified. And if it fails any one of these stages, the entire system fails. All right, so for the first part, hash is a deterministic one-way function. This just means that it's infeasible to invert from the hash back to the original data. So the same message always produces the same hash as hash functions are supposed to work. We need the original message to compute this hash, so it should be infeasible to find another message with the same hash value. At the final stage, it makes it impossible to verify that the message didn't change, since the entire entity holding the private key signed it. And this is the basic underpinnings of the cryptographic security provided by the TPM, allowing us to verify that the firmware image or the update push to the system was signed by Apple or signed by any other device that provides this firmware signature checks. Okay, so this is just a general diagram of how this might work in the real world. So you have cryptographic coprocessors, which provide RNGs, RSA keygens, SHA-1 hashes, encryption, decryption, verification. You have memory, you have different NVRAMs for secure cryptographic key storage, and all of this should be separated out and verified or protected at a certain level. And so we have a bunch of hash values. What's next? So we check that everything seems normal. So the signatures should match and they should be able to be trusted by a trusted authority. And so we should finally extend that the PCR values measured for a specific state actually work. So this is just a simple diagram of how this might work between a TPM, which is physically separate or should be physically separate from the host. However, this isn't perfect. So we can do something called a PCR extended attack. So this diagram from NCC Group, or a tool from NCC Group, allows us to actually perform an attack in between these two processes. So I think the one key takeaway is that people forget that hardware is hardware, and there's a physical part in this equation between these two components in which things can actually be injected or physically modified. And this is what this tool does here. So this is the GitHub link for it. But the TPM Genie, which is what their tool is called, is capable of intercepting and modifying all traffic that is sent across the I2C channel, so between the host machine and a discrete TPM chip. So many discrete TPMs are broken out to a daughter card that is connected to the main board via a simple header or socket. Consequently, the process of implanting interposer, so that's this thing here where the fun happens, is fairly straightforward, as it would not require the attacker to perform any circuit modification, which we kind of see here. So we could just plop something down in between it. Maybe it would take a second or two and actually perform an attack. And this is something we could do. So we could replace the SHA-1 hash in transit with an attacker controlled value to allow our non-validated code to run. So the example would be a firmware update gets sent down to the host. The host says, okay, TPM verify this firmware for me. The TPM takes the SHA-1 hash, sends it back to the host, and the host checks it. And through this interposer, we modify the SHA-1 hash in transit. So something we could do here is simply add a software backdoor that makes sure that if there's an evil hash, so that would be our payload sent down to the host, that would actually be compared against, and then our good hash, or the one the host is expecting, would be replaced with it. So this is an example of a physically enabled software backdoor, which is most common type of attack in this world. And so the example kind of like this, so the TPM would send back, no, this is invalid or something, but in this case, with our software backdoor, it would send back, a good or valid hash, and the host would load it to the system, and you would now have your controlled malicious update running on the host. And these are, so CVE 2018 uses this technique through a power attack, resetting these PCR values. So that's one type of method. Bus tapping is also a different attack that has the same effect. And you can recover keys after watching the bus. So there's many other alleged attacks like this through power analysis, backdoors, malicious update files, Google iPhone backdoors, and they all kind of rely on the same core principle that I mentioned, which is that physically things are separate, and physically you can't verify the same software security properties as it goes across the line. So your hardware security is only as good as you can physically protect it, which in this case you can't once you send it off to the consumer. So some types of attacks like this are Operation Shadowhammer and Shadowpad, which came out last year. Shadowhammer came out in 2019. And the interesting thing with this one is that the payload for this software update actually only launched when specific MAC addresses were hit. So when specific MAC addresses were found, it would actually launch its payload. It's still a mystery as to where these MAC addresses were recovered from. So how did this malware actually know which of its target computers had what MAC addresses without access to the manufacturer or something like that? But that's an example of using the physical properties of the system in its software backdoor. And then Shadowpad is one of the largest known supply chain attacks, and that was from 2017. And that's where a server management software product was actually backdoored. And so the update there, though it should have been trusted because it was technically the proper server managing the updates, was actually compromised. So this is just an example diagram about what actually was going on, where it did the actual check and launched into the payload on ASUS platforms for specific computers. And this is just a diagram of the Shadowpad attack with the malicious update management server. So I rushed through those mostly to get to this example, which I literally added 30 minutes ago. But a friend of mine, his name's Gabby at White Ops here in New York, released a new backdoor that was uncovered and released today for mobile browsers through this Android phone. So this is one of the largest Android mobile giants in China. I'm going to pronounce it wrong, Xiaomi. And basically the backdoor was placed in one of the system apps. So phones are usually, Android phones are shipped with a browser. So Samsung browsers on Samsung phones, Android browser for this device. And this backdoor provided functionality as the browser, as a browser, so that was normal. The user wouldn't notice, but it also provided full control and full surveillance of what apps were being opened, what data and content was read on the browser and uploaded to the internet through the browser back to a server in China, specifically an Alibaba server. And so this is the code from this browser. You can see it here. If anyone's interested, it's in this class. So if you just decompile the APK for that, which is shipped by default on the phone, you can see that this is the load event hooked and added to a hash map. So the load event of a URL inside of a tab. And so once you hit enter or open up a new tab, this event would be triggered. And this is the equivalent for the load event finished page, where it said, okay, the load event's finished, grab all the data from the website and ship it back home. And this is just the code that actually does the sending back home part. And if you pop this open in your favorite network browsing or sniffer, you'll see it actually posting it back to its Alibaba server and encoded and encrypted like this. And And that would be any data that you put online or any app data that you're performing on unprivileged, so untrusted apps on the Android phone. So this is another picture. Apologies, that was not my URL to browse to. So, and this is an example of a backdoor that's shipped with the device. So it would be not in the firmware, but in a application that's specific to the default setup and integration of the device firmware. So the default settings of the phone. And it would provide data of any sort of behavior or content back to the server. And yes, so this was the discussion of how the app would send, or the backdoor would send app data back as well. Oh, there we go. Okay, sorry, everyone's seeing the chat now. Right. So now we have different types of attacks laid out. So we have sandwiches, we have ads, so things that are put on PCBs, things that are put inside of chips, or in between chips layered inside of the same package, which are probably very hard to do. But we also have things that integrate with the system itself. So potentially something that's snipped from the TPM and added as part of the, like the boot check on a firmware update. Or we have something as simple as a backdoor put in the default firmware. So this diagram just kind of lays out the different stages of design and supply chain before it actually reaches the consumer. So if we look at stage one, a specification is developed at this stage. So this can be easily checked at the stage for backdoors or other failings in-house. So this is when Supermicro is developing their code and their design in-house in California. They can easily run things through verification checks. They can look at the code to see if anything's been changed. It's the easiest in time as well, though, to insert a low-level hardware backdoor. So if you do control this process and you do control parts of the verification stage, this is the point in time that's easiest to insert the backdoor. So in stage two, we start to reduce the specification design to practice. And then we get to three, 4, and 5. And this is when we're manufacturing. And so this part really happens through multiple third parties. And it's not easily checkable for security properties. And it's also difficult to insert your backdoor at this point in time. So for example, Supermicro uses a company, I believe it's called Ablecom. And fun fact, Ablecom's owned by the brother-in-law of the owner of Supermicro. And they actually send out their design and manufacturing and supply chain logistics to multiple other third parties to do all the different sub-development components of the entire process. So it's very hard to determine where failings happen at this stage or what's going wrong or what's going right. Just introspection in general. So third-party hardware and firmware integration also leaves room for backdoors and other flaws to enter into this equation. So we have integration of libraries or chips that have already been developed by companies, so perhaps a TPM chip or other parts of the hardware design itself, where you just incorporate things that have already been built. And you might not have source, or you typically don't have source code for this, or the actual specs for the device. And those sort of secrets are kept very tightly in-house. So it's very hard to get those details. And so by the time you're at stage 6 or 7, the manufactured device reaches distribution. So it's in a warehouse or in transit to a customer. The company and customer have less ability to claim the device that's actually going out matches the original that was developed initially. And by the time you reach stage 7, when the user is controlling it, defense largely depends on end customers' physical security and processes. And so are they storing their servers in a third-party warehouse that holds servers as a business? What are they actually doing with the device? So the end point that I really wanted to make for this talk and in general is hardware backdoors don't operate alone. Take, for example, Trammell Hudsons PLC, or proof of concept backdoor, which he published at CCC Congress 2018. So he used hardware to set configs on boot, and then specific firmware parts of the backdoor would then take action to do networking or to do whatever collection you'd want to do at that point. And then another great example that we can get to from here is Huawei. So for binary equivalence, which is when you want to check that the firmware that you get on the device matches the firmware that's intended, Britain actually had a pretty big problem for this. So specifically for Huawei base stations, they have something called HCSec, which is a group that looks at critical systems for security issues, so specifically for Huawei, and they were given incomplete source to audit for security properties before the UK actually purchased Huawei 5G equipment. And so they determined that unless it is possible to build and actually verify that the source code they received built to the same firmware that was running on the device, it was basically impossible to verify that the code matched it all. We'll talk a bit more about that in a little bit. But there's a few different stages of how you could perform this. So you can look at the source code. So an attacker could hide a subtle logic bug, so a backdoor or something similar. And this would require multiple preconditions or failures on the auditor part. It is difficult to audit for security flaws in this, especially when the general code quality is poor, which was the case with the source code that the British government received. We'll look at some examples in a second. But you can also look at compiled firmware. So you can take your router or device, pull the firmware off of it, and see if that firmware matches what you could reproducibly build from the source code. Also, you could look at the build chain and how it does the signature checks as it goes along. But it's hard to do this when these different components aren't available for testing purposes. So we can do reverse engineering and program analysis to try and align parts of the binary firmware with code. And this is what we ended up doing when we were actually auditing some of the Supermicro binaries. But it is still difficult to say with 100% certainty that you're looking at the same thing as the source code is. So doing the binary equivalence there. Yeah, and so also you can look at what data is already on the chip when you receive it. So specifically here, even reading differences between zeros and high bits or Fs in memory and firmware. So there's always differences there. And this was a huge issue for us when we actually looked at a bunch of different Supermicro products that a customer of ours had purchased, and they were afraid that some of these might have contained the alleged backdoor. And so we looked at the firmware we pulled off of it and the memory we pulled off of different devices over a series of years of purchased devices to see if what has changed, if anything. And so that's one measure you can do. I just have to call this out quickly. So for Binary Ninja fans out there, BinDiff has now been released for Binary Ninja, and this is a huge godsend when it comes to binary matching between firmware or between things that you might want to check for changes in. So what we do in-house, so in joint work with Riverloop, we have a product called Pilot Security, and we actually use extensively Binary Ninja to look through firmwares at scale. So we pull the firmware off of hundreds of thousands of devices and run these through different checks. You can check for things like passwords that are set. You can look for things like hashes and things that it might match against. We find situations in which the firmware is actually matching against a hard-coded MD5 hash to check for signature updates or firmware updates. And we can also find things just simply like vulnerabilities. So, vulnerable C functions, store copy, printf, system, memcopy. These are scattered throughout the device. And you can make sure that the system that you're running on actually is secure or not. So there's limitless possibilities about what you could check for, but similar to malware analysis, once you've detected a pattern of vulnerability on the system, you can scale that up and check it over hundreds of thousands of devices. But why would we want to do this? Well, looking through large programs is pretty tiring. So doing this automation is much faster. And so like I said previously, manual is good for finding issues such as logic bugs or very subtle changes to the source code. But once you found that, those subtle changes, you can encode them in a program analysis pass and actually check for them at scale. So how is this device firmware interacting with NVRAM? Does the device ship with content in these memory locations that it's expected to be there, and pulling from the system into the firmware to use at runtime? And so things like that you can automate up and pull those values out to see if they are malicious or not, or to see if the security failings of the device are as bad as you think they are. Usually they are. But yeah. And so if you actually look at the Huawei base station source code and run these sort of checks through it, you find that at compile time, things look a lot different than at source code tab or when you're reading source code. So for example, this was one case that was also found through the UK working group. They had a wrapper around safe library memcopy, which literally just called into memcopy. And so in this case, at source code evaluation time, you'd see a call to safe library memcopy. And as a reverse engineer or auditor, you might say, okay, so they're probably using safe memcopy. They use destmax, count. They probably do all the checks. They probably pass it to memcopy safe. They do not. So at compile time, this function call is swapped out with memcopy, and that's the actual value you get. And as we see here, destmax is just thrown out. So this is sort of bug that you might only pick up at the binary evaluation time. Similar thing here. So oftentimes you'll see embedded devices ship source code packages with dozens of copies of the same library. So in this case, there were 70 full copies of 4 different OpenSSL versions, even ones of like 098, which is extremely old if people aren't aware, and then fragments of many other versions. And so at source code evaluation time, you might say, okay, they ship with a bunch of these old ones, but which one are they actually using? That's something you'd pick up from just being able to build the software and audit it. So this was a pretty egregious compile time bug. And just going through a few different other examples, which we presented more at length at Echo Party through a talk with 20 devices in 45 seconds. Through automation, you can simply detect things that, there's a password entry that's hard-coded in the firmware, and that's easily decryptable. So black those out, but that's a pretty common one that we see in a lot of devices. Additionally, even more issues with accounts that shouldn't be there that are, or hard-coded passwords, hard-coded access codes, things like that. You also can encode checks, and one of our checks does this, that to see if there's any changes with hardware interaction. So is the device being shipped now with a new chip on it? Is the interactions with that chip different than what they were previously? So we might not even know what the intentional or good interaction with, like I said before, NVRAM might be, but if there is changes to it, we should take a second look at those. Also, failure to patch is another huge one. You see that a lot in devices as well, and that's something that also can easily be checked through automation. Like I said, lack of encryption. Specifically, this example is one where I don't know if they forgot to, but they didn't patch a command injection bug through a parameter MAC request. So you can just see here that you can simply send your, command injection command, like for example, telnet, and it'll execute things that way. But, and these are some examples of ones that we didn't find ourselves, but are also pretty egregious. So specifically, here we saw that the MateBook laptop series early last year actually was shipped with a binary that wasn't part of their source code release, but it was a backdoor on their Windows operating system, and Microsoft Windows Defender actually detected it. So when people booted their laptop up, they would see that there was this, huge warning, and so it turns out they actually had a rootkit shipped with the physical devices of the laptop that Windows Defender detected. So a few months later, they took those off the market. Funny enough, before the actual trade ban was announced. So yeah, in general, as we can see from the Supermicro case, hardware backdoors themselves are very hard to prove. You can't just simply look at an X-ray and determine that one layer in a sandwiched chip is bad or good. Or you can't easily tell that one connection through silicon via is connected to something that it shouldn't be, unless you have the full specs of that chip design from the manufacturer, which, unless you work there, you're probably never going to get. So a true hardware backdoor is undetectable in general. And so the big example there is the factory swapping out parts to put in cheaper parts, sometimes because they can't get the more expensive part, sometimes because they can sell the more expensive part and pocket that extra few cents from the cheaper part. So at the end of the day, if you control hardware fabrication at any really point in stage in that diagram I showed, you really control the device. And you can control what things are actually connected, what operations it's actually performing.
Sophie, we are almost running out of time, so yeah.
Yep, I'm almost done. I know I'm running through this a bit quick, but I wanted to get it all in. I won't go through all this then, but these are different.
You could continue if you like, but for a minute or not more than that. So then we can take some.
Yeah, so these are just other design pitfalls we can come back to. Also design pitfalls, practical steps if you want to learn more to implement appropriate testing and things like that. And then any questions? Just putting this out there, this is an X-ray of one of the Supermicro chips that we looked at. And you can see here that we're looking at what different components are there and what doesn't make sense, or do any of them not make sense to be there. I guess one more technique that I'll mention before I open to questions is one thing we like looking for is a component that we assume should be a passive component, is that actually an active component? Because as we see through a lot of backdoor proof of concepts and things like that, oftentimes you can package up a active component that looks and acts like a passive one with extra features. And so that's a good kind of binary check to do on parts. And then with that, I will open up to any questions on the floor.
You should receive questions in your chat. Sophie, your audio is mute.
Oh, sorry. So how does the DoD protect itself against these attacks? Who are the people involved and what are the tools they use? Honestly, the best way to protect yourself against hardware implant attacks or hardware backdoor ones is to really trust the entire supply chain. So I think the biggest problem that I see is that when you ship the design off to that the first party manufacturing, they then ship it off to 10, 20 other sub-manufacturers to do different development components. And at this stage, you really lose all control. So if you can nail down exactly what's going where and who's touching what component and what third-party parts or designs are used, then you have a better chance at protecting your supply chain. Can you have the slide with resources back up? Yes, I can. Sorry about that. believe this is the one you were talking about. Okay. Let's see. Yep, so a few of my slides I actually mentioned were taken from ideas that Bunny had mentioned. So yeah, I recommend that everyone watches Blue Hat Talk. He goes into depth at what the real cost is to attackers and to defenders for each different type of attack at each different stage of manufacturing. Where do you think the future X-ray 3D reconstruction algorithms will take us? Iterative reconstruction, machine learning can further increase the capabilities of X-ray images for PCBs. Yeah, no, I think this is actually a really interesting one. I do not own any Chinese-made devices. I strongly recommend buying an iPhone. Yeah, so I do think that the future of X-ray imaging can help us break apart even further where things are going. And I think other different types of imaging as well. Basically anything that we can do where we don't actually have to sit and delayer each layer off of the chip to get a good image of things.